looks like it's starting up pretty quick. So Adrian, did you have a particular reaction you had in mind from the videos for today, the three-member ring things that you wanted me to look at?
No, nothing in mind. These videos just help out a lot.
Okay, let me...
When you're watching them after the lecture vids.
Right. So let me... I think the best thing to do then would be to talk about bromohydrin formation. Because the bromohydrin is an important intermediate on the way to epoxides as well. And epoxides are important reagents because the three-membered ring has ring strain, which means you can convert epoxides into lots of other things. So bromohydrin formation. So it's just a CC double bond. I'll use a tri-substituted double bond as an example. And I'm putting it in a cyclohexane ring so that we can see the stereochemistry. We know that these are anti-additions because all of the additions that go through three-membered rings are all anti-additions, and I'll be able to see the anti-addition if I tie the double bond into a cyclic system. So the reagent is bromine, and the solvent is water. And in this case, it's the solvent and the nucleophile. Water and bromide are competing as nucleophiles, but since there's so much more water present than there is bromide, water is going to win by just a concentration effect. So mechanistically, what we're looking at with bromine is very similar to what we were looking at with the mercury. We're looking at a polarizable molecule, right? So bromine can polarize, these electrons can kind of shift over to the other one and build up a partial positive charge, but we're also looking at a nucleophilic lone pair. So what we have is an atom that can behave as a nucleophile and as an electrophile simultaneously. The double bond is going to attack the bromine, and that'll attack at the less substituted end because the electrophile always goes to the less substituted end. Right? Markovnikov and anti-Markovnikov addition, the electrophile still goes to the less substituted end. It's just a matter of whether the electrophile is the big thing or the small thing. And then the lone pair on bromine can attack the larger delta plus charge. Normally we don't show the transition state for this, but I'm going to show it anyway this time because I think it'll be useful for you to see that we're actually forming bonds to both carbons, and we're breaking that pi bond, and then we're also breaking the bromine-bromine bond. So we're building up a partial negative charge on the bromine that's leaving, and we're building up a partial positive charge in that ring. And when we're done, we have a bromine, and I'm attaching it to the bottom face, but there's no difference. We're going to have a racemic mixture here. So it looks like that. And this is the bromonium ion. The formal charge is written on the bromine here, but it is actually distributed through all three atoms on a molecular orbital theory, and there's a larger delta plus on the more substituted carbon because of hyperconjugation to the methyl group than there is on the one that just has that hydrogen there. Right? This is a tertiary carbon, this is a secondary carbon, bigger partial positive on the tertiary carbon. So I've drawn the bromine on the bottom face, and we have bromide ion. If we were in a nonpolar solvent, a solvent that was not capable of behaving as a nucleophile, this bromide ion would be what opens the three-membered ring. But in this case, we have a solvent that has a nucleophilic lone pair, so the solvent can act as a nucleophile, and as I said, because there's way more water there present than there is bromide, this is going to outcompete. Right? This step obviously depends on the concentration of the nucleophile, since the nucleophile is doing the attacking. So we're going to attack, and we have to attack from the front, from the top, because the bromine is on the bottom. Right? So this is an SN1-like process, but it's still stereospecific because this leaving group isn't really gone. The leaving group is kind of still attached. So that inverts the stereocenter at the tertiary position where the attack takes place. And the positive charge now ends up on the oxygen because we form that third bond. At the secondary carbon, we haven't changed the carbon-bromine bond, so the bromine that was on the bottom is still on the bottom at the secondary position. This isn't neutral, so to make it neutral, we do a proton transfer reaction. And that will end up forming what we call a bromohydrin, where we have a bromine and an OH group on adjacent carbons. And you can see that it was an anti-addition. And this is also racemic. And you can see that it was an anti-addition because the bromine and the OH that we've added are trans to one another, right? Opposite sides of the ring. So it's kind of similar, right? We got 3 steps. The first step is the formation of the 3-membered ring. The second step is the opening of the ring. Sorry, this is still step 1. And the third step is a proton transfer, which is identical to what you saw with oxymercuration. The difference is the electrophile here is bromine as opposed to a mercury atom. But the second and third step are identical, opening the 3-membered ring with water and then doing a proton transfer. That bromohydrin is useful because since it was an anti-addition, the OH group is opposite the bromine, which means it's held in exactly the right position for an intramolecular Williamson ether synthesis. So if we now treat this with KOH, or sodium hydroxide, doesn't really matter. KOH is a little bit more soluble in the nonpolar solvents. Aqueous base, we can actually deprotonate the oxygen. That's an equilibrium reaction. The equilibrium constant is about 1 because the OH group on the ring has a very similar pKa to water. But this next step is not an equilibrium. And you'll notice that this oxyanion, the alkoxide ion, is on the back side of where the bromine is. Right? So it's opposite the leaving group, which means it's held in exactly the right position to do an intramolecular SN2 reaction where it comes in and pushes the bromide out. This is a Williamson ether synthesis. And because the 3-membered ring is very favorable kinetically, right, that oxygen is very likely to attack because it's right there. And you'll notice we invert the stereocenter here. We don't affect this one, right? This stereocenter remains the same. So we've made an epoxide, and this would also be racemic because the initial attack on bromine, because that's a planar molecule, can happen equally at the top face and the bottom face. So this is a way of making epoxides. And if you had a difference in the steric, right, if you had something like this, where now the top face and the bottom face are different in terms of their steric requirements, right, the top face is now less hindered than the bottom face because the bottom face has those 2 hydrogens. You can actually get selectivity. So it's stereospecifically anti, right? Because the three-membered ring requires the nucleophile to come from the opposite side as the attack on the electrophile. But it can also be stereoselective for the less hindered face. So the bromine would attack on the top face because the electrophile always wants to come from the less hindered side. And once you selectively form that bromonium ion on the top face, right, so that's on the less hindered face, whatever the less hindered face is, then that determines the position of the alcohol. Because regardless of where the bromonium ion is, the nucleophilic water has to come from the side that it isn't, right? So in this case, the nucleophilic water would have to attack from the bottom, pushing the bromine out. So this is stereospecific. Right? The mechanism requires that the bromine and the alcohol are on opposite sides. Right? We're going to invert the stereochemistry here, which means our water will have come from the bottom, and then we'll do the proton transfer. Where water takes one of those hydrogens off. So I'll end up with the OH group down and the bromine up, CH3 up. Right. So it's stereospecifically anti, but it was stereoselective for the bromine on the top less hindered face. And it's also regioselective. Selective. For the nucleophile attacking the more substituted end. So you've got stereospecificity in the ring opening, you've got regioselectivity for that ring opening at the more substituted end because of the larger delta plus, and you've got stereoselectivity in the bromine attacking on the top face, which was less sterically hindered in the first place. So there's a lot going on in bromohydrin formation. If I were then to treat that with KOH, I would end up with my epoxide on the bottom face of the molecule. Which is the more hindered face. Does that help?